All right. Yeah. Hi. Hi. Hi, Jade. Hi, Yuting. Hi, Yo Xiang and Qiandi, Shengdi, as well as Xuan. Mm. Good to see you all. And let's go over the to-dos this week. So we do have 3 quizzes doing this week on Saturday. And the exam number 1 is coming next week. So tomorrow during the break, we'll borrow a little bit of our break time to go over how we go about doing exam 1. Okay, so try to attend at least the break part of tomorrow. And so in case you have questions, anything that's a little bit too fuzzy for you, you can definitely ask right there. Okay, good. Oh, I see Wei Shan and Yuqi. Welcome. Now, let's move on to the first topic today. So we are not quite yet done with the HTTP protocol, particularly the format part of it. So last week we talked about the request messages, and we had a quiz, isn't it? Today, similarly, we're going to talk about the response message, the message that the web server generates and sends back to the client who requested for the web page. So, how the response message look like? It's actually somewhat similar to the request, 3 parts as well. Now, finally, the HTTP response message. Okay, the second type of messages defined in the HTTP protocol. You see here, generally, 3 parts. First, the status line. Second, the header lines. And the third, the data. So the entity body, so to speak, from here and down. Okay, and these are very similar to the header lines we see in request message. Each line, you see attribute and the value. Attribute and the value. Status line. 1, 2, 3. Again, 3 components. Let's go through each one of them as well in a bit more detail. In status line, first here, familiar. So the version of HTTP the server is implementing is the first component in the status line. Second, this is the status code. Okay. So in HTTP, it defines quite a number of these status codes. Each of these indicate a different condition. Okay. Some more related to the server, some more related to the object being requested. Okay. And for each of these status code, there's a status word being shown as well. That's the third component in the status line. So 200 here indicates okay, meaning the HTTP server is working well and the object you're looking for has been found. And it's going to come here in the body entity. Now, second part, the header lines. We see date. Yep, this is the date, time, the request is being filled, and this response is being generated. The server, this is an Apache server, version 2.0.52. Apache is one of the most commonly used web server implementation. Yeah, I think you heard about the other one, Nginx. So Nginx is certainly rising. Okay, it's not quite yet the most popular one. Well, let me clarify. By popularity, I meant the number of machines running a specific version of web servers. So Apache is still the most used web server. But if you count only the number of downloads recently, it might be Nginx. That's why you see I say that it's actually rising. So I think maybe in just a couple months, there'll be more Nginx server than Apache servers. Last modified. Yeah, so this is to indicate when is the object you're downloading last modified. Oh, okay, it's a really long time ago. All right, ep8. What is this? This is actually, hey, for each version of the object that you are downloading, there comes also with a version number. So ep8 there is to indicate the version number. Nowadays, as you see, the HTTP protocol is not used only for downloading purpose. It can also be used for uploading.
if there are multiple users there using different web browsers trying to upload the file, for example, poly and Caleb, the TA, tries to upload and override the grades Excel file, then you might have a consistency problem there. So the number here is to break tie, to make sure that a newer version does not override an older version or something like that, to resolve conflicts, so to speak. And accept range. Yeah, yep. So, you know what? Earlier when I mentioned the head comment in the HTTP request message, right? So when you send such a comment in the HTTP request message, the server responds with only the status line with the header lines, but without the data. Okay, so server there can actually tell the client, you know what? I'm a server that allows you to request content in terms of bytes. So the client there seeing this can then send the request more officially, instead of using the head command, using the real get command, and request to download byte 0 to maybe 1023 or byte 0 to byte 100. Okay, so you could do a range request in a way. And the server's next header line, content length. This is to indicate the size of the file or the size of the object that you're downloading. So you see the file size of the object is one critical parameter. Okay? If you're implementing a web server, you need to know a way to find out what the file size is or the object size is. Okay, the size is a bit messy. Let me clear the markups. Keep alive. Oh, good. This web server implements persistent connection. Okay, and so it indicates timeout interval is 10 and maximum 10 requests. So this is a persistent connection, but in the connection, it only accepts up to 100 requests. All right, so if it's more than 100, then you will force close. The server will force close the connection. So connection, keep alive. Content type, yeah, just like the client size header line we see. Yeah, the client accepts content of a certain format. Here, okay, this is to indicate the object the client is asking for, which format it is. And we see this is text-based HTML file and it's coded in ISO aa59. Right? And empty line, indicating this is the end of the header lines. Right after the empty line, the data goes here. If it's an HTML file, then hey, text starting from here. Okay, the first file. So this is an example of HTTP response message. You see the structure is very much like the HTTP request messages. Next is just to share a bit more. HTTP response messages status code. We've seen earlier in the example, 200 OK. This is saying request is successful, object is already embedded. 301, that means the server is saying the object is moved to a new location specified later in this message. So sometimes when you run into a message like this, you see, oh, click here. That's going to take you somewhere else. It's a redirecting link. If you see status code 400, that means your HTTP request format is not quite correct. Bad request. 404, that means the object you are asking for is not found. 505, HTTP version not supported. So in case you're using a very old browser, or if you're contacting a server that's very old, and yet your browser is implementing something newer, then you might not be able to communicate. The server is going to tell you this. Sorry, 505.
All right, so that was the response message. So you see that in the request message, we have the command line for the first part. In response message, we have the status line for the first part. Okay, both of them have 3 elements, but this is to issue comment and indicating where which object they are looking for. But in response, it's more to tell the status of this request. Okay, is it okay or is it bad? Second part header lines, very similar. You might see some header lines being the same. The third, the request part, it doesn't have any data. Okay, but in the response message, you see the actual data, the web objects coming. Okay, good. And that takes us to quiz 11. Very similar to quiz 10, we also sniff a HTTP response message, and this is how it looks like in the box. Q1 asks, was the document being requested found successfully? Okay, can you tell from the response message whether it's successful and how? Q2, how many bytes are there in the document? And where did you see that? Q3, what are the first 5 characters of the web object that's being downloaded? And where do you see that? Okay. Oh, okay, good. And this is a very simple quiz, very similar to quiz 10. So you have only 2 minutes to work on this. Okay, so let's go ahead and start. Yeah, all right. I can tell that the quiz is super easy, isn't it? Yeah, so the request is successful because you see in the status line, it says 200, okay. And the size can be found from the content length header line. And the first byte of the document, yeah, so right after all the header lines, there comes the document, right? So the first 5 bytes, 5 characters of that document will be the first 5 characters. So let's make sure that we see the data, the content. Yeah, so this is the last line, isn't it? CR and what is that? LF, yeah. Cartridge return and line feed. Okay, that will be the /n/r or /r/n. Yeah. So the first 5 characters will be the less than sign and then exclamation sign and then DOC. Okay, good. So you've got it. Very good. And so we can then move on to the second topic today. So next Polly is going to demonstrate how one can use existing programs such as Telnet to send a web request message by typing it up from keyboard. And a real web server is going to generate a response according to the web request you send. Okay, so here's the setup of the demo.
So what I will show you in the demo coming next is to do this. Telnet to the favorite web server here, and we're going to use this machine here that the textbook author has set up for us. So we'll telnet to gaia.cs.umass.edu at port 80. Okay, what it does is to open the TCP connection to port 80 where there's a server already running, a web server already running. And anything typed in will be sent to port 80 at this guy. Okay. So Telnet is a remote logging application. just like SSH or RSH, if you know what it is. It's another remote logging command for native Unix users. All right, so Telnet is very, very old. Many operating systems probably doesn't support it anymore. But I've already installed it on my Mac, so we're going to show that in a little bit. Now, once we telnet to the web server, and we'll type up some things. Okay, let's try typing this. Get path name and file name as the argument for the get command, and then the version of the web browser. So we'll be pretending that the telnet here is a HTTP 1.1 client, and host gaia.cs.umass.edu. Right, so header line. So essentially, we are trying to do a human web browser, okay, by typing online right here an HTTP request message. So once we are done with this, we hit return, okay, and then we hit return again. Needs to have a what? A \r\n here in order to complete the HTTP request. All right, so the whole thing is going to be like this. And yeah, we'll see what pops up in return, what the server there at umass.edu sends back. Okay, let's not sniff the traffic. Let's just look at the response coming out of the telnet program. All right, so let's switch to the demo mode. All right, let's telnet to gaia.cs.umass.edu at port 80. All right, connect it to gaia.cs.umass.edu. Now let's pretend to be a web browser. Get. Oh, wow, that's pretty long. The path and file, pretty long. Let's copy it from the slides. And over here and print. All right. And then host poly.ntu.edu. How about that? All right. And one more empty line to indicate this is the end of the header lines. There we go. Wow, it's returning a lot of things. Scroll back, and scroll back. Wow, very long in fact. But it looks like it's an HTML file, right? It's an HTML file. Now, this is a hyperlink to an text HTML file. Okay, let me scroll a bit faster. I don't know how long this is. Oh, there we are. Yeah, so we typed up this line here. Okay, and we also say we are host poly.ntu.edu.tw and an empty line and then return again. The whole message gets out to the web server at gaia.cs.umass.edu, and the web server returns this http://11 to the 200. Okay, and header lines number 1, the date. Header line number 2, the server. Oh, it's an Apache server. And X powered by PHP. I see. Content length, content types. And hey, empty line to indicate this is the end of the header lines. And starting from here, the real body. Okay. So we get the output of calling this PHP query at this path. Let's see, interactive problems, computer networking, a top-down approach. Oh, okay. So this looks like the main page of all these interactive exercises that we see every now and then on the slides. All right. So there, essentially very text-based interaction between the client and the server. As human beings, we could also do it right here, right now, online as a web browser. All right. Good. And I think let me just go back a little bit here. You see here, 200 is a very classic example of the syntax defined in an application layer protocol. In HTTP, to be exact, 200 is to indicate OK. So OK here is just to say it explicitly, the semantic of 200. Right? So that concludes the messages format, semantics, and syntax of HTTP.
All right, so we are finally done with all the basic components of the HTTP protocol. The next two topics are more the add-ons of the HTTP. And the first one is called cookie. I don't know about you, but recently when Polly go to random pages, I get a prompt a lot to try to configure my cookie settings. And it's getting a little bit annoying. Okay, so let's find out how cookie works first.
Next, cookies. Yeah. Many websites these days will try to prompt you to set up cookies before they allow you to visit the website further. So it's very, very relevant to our everyday life. Let's see how it works. Okay. First thing is, the cookie setup process is always initiated from the website. So meaning from the web server that your web browser is requesting objects from. So web server there is going to send a message to the web browser carrying a special header line. Okay, it's the cookie setup special line. And the web browser there, upon receiving such a message, it's going to generate a corresponding message if you click OK to insert cookie. And that message is going to carry, again, a special header line saying cookie OK. All right, so exchange of messages between cookie setter and cookie allower. Now, when you say, OK, I will allow setting of the cookie, your browser is going to add an entry to the special cookie file on your local disk. Okay. So that is exactly what's expressed here in the special cookie setup line. And when the server receives the message allowing cookies, server would then add a special entry as well to the backend database. And that entry set up here and here will actually map to each other, allowing the server to identify who you are and when have you visited the website last time. Okay. Let's use an example to explain. It will work slightly better. Let's say Susan always accesses internet from her PC. And she's visiting a specific e-commerce site the first time. In the initial HTTP request, that arriving at the server, the site will then create a unique ID, and that will be an entry being added to the backend database. Right? So that ID is going to be carried. In the message, the site sends back to Susan. So that's going to be set cookie and then the number created here. All right. So local hard disk you have there, or Susan has there, will have that entry set up in the cookie file. So this will go back to the server, carrying also that special ID that Susan has already allowed to set up. And then at this point in time, the server would finally enter the entry to the backend database. So that's the way it works. Let me illustrate, and so that you know clearly what's going on. Client, server, or Susan, Amazon.com. Now, at the client side, you have this special cookie file, and it's managed by the web browser. And you might have clicked OK to eBay. So eBay has already set up a cookie entry carrying unique ID 8734. Server here has a local disk as well. It's maintained more as a backend database instead of just a simple file. Right? So, but when you visit the website, Amazon.com, the first time, you send an HTTP request message. Now, of course, you have not yet been in Amazon before, so there's no entry for the Amazon website. So in your initial HTTP request message, there's not going to be any cookie special header lines. All right. So when Amazon.com here receives HTTP request, of course, it will try to grab the objects that you're looking for and try to generate the HTTP response with it. But in the meantime, it will be creating an ID for this particular user, and add that to the database. And in the response, it carries the web object that you're looking for, but it also carries the special header line, the set cookie line. And hey, see the ID created is carried over through the HTTP response message back to the user. So web browser here sets up one extra entry saying, hey, for Amazon, the website, use ID 1678. So for the subsequent visit, subsequent browsing, all the HTTP request messages is going to carry the cookie OK and I am user 167A header line. Right? So Here, the server, of course, will be generating the web objects, generating the HTTP response message that you're requesting with the request message. So, response message. But the response message might also contain additional content. Okay, server there could be seeing your browsing history a couple clicks back and discover that, hey, you might be looking for a specific item. Okay, and then recommend potentially items you'll be interested. Okay, so that might also be part of the response messages. So showing the items you are looking into buying as well as related products. Okay, so for example, if you're looking to purchase a phone, then the website might be recommending a phone case, okay, or a number of phone cases. So what's amazing there is 1 week later, okay, when you come back and try to purchase something from Amazon again, okay, the first request message you'll be sending will already be carrying the cookie entry. Okay, so once you have it set up locally on your cache file, on your cookie file, for all the subsequent HTTP requests, it's gonna by default carrying the cookies. Amazon here will know, yeah. So over time, the server will know, probably your profession, probably your income level, things like that. Okay, so that's why it gives people a certain creep about setting up cookies, and you might be warned, be careful about setting up cookies there.
Yeah, so cookie, it's actually good and bad. So next, let's discuss cookie a little bit more.
Now let's discuss cookies a bit more. We're going to talk about the trade-offs of using cookies. First, the cookies from a business perspective, from a website's perspective, is actually quite convenient. So you see, you can authorize the users quite easily, okay, by looking at the ID in the cookie header line. Tracking the shopping carts as long as the ID is the same, right? This is items purchased from the same user. You can recommend items so that the users will go, wow, cool, that is exactly what I was looking for next, right? If the user is purchasing a phone and the website suggests purchasing of a phone case. Yeah, and browsing emails, yeah, you will not want to try to log in and type up password again and again. You want to be able to maintain that email reading session, email sending session over time and log in just once. How? Very nicely through the cookie line in the HTTP request. Okay, quite convenient. Okay, otherwise, you guys, including Polly, when I read my Gmail, I have to log in again and again and again. There's no way we could live like that. Right? So convenience. But on the downside, those websites would be able to learn a lot about you. Okay? So you store emails, that's pretty much your personal life. You store your purchases there, that's pretty much also your personal life. Okay? So over a long time, you can imagine Google, Amazon, Facebook, all these major websites, they know a hell lot about you. That's why people are freaked out so much about these big sites, okay? Allowing them to set up cookies, allowing them to store information about you, okay? So, downside, privacy, okay? Now, another perspective is more technical, keeping states. Now you see, hey, there's ID on the local cookie file. There's ID stored at the server side, the backend database. So, server and clients are now storing states of each other, about each other. But some of you might go, hey, wait a minute. Didn't we talk about HTTP being a stateless protocol? And what's nice about stateless protocol is that, hey, none of the endpoints need to store anything about each other. Okay? No storage requirement. And you don't have this problem where, hey, if the connection between the client and server is broken, and you might have these inconsistencies in the states they maintain for each other, right? You have to reconcile and resolve conflicts. And that is actually a very, very hard problem, okay? Who do you trust more, the server or the client? Okay, sometimes it's a bit hard to say, okay? So cookies here, you're seeing is, in a way, a hacking HTTP such that we can maintain states, because HTTP was not designed in the first place to maintain states. But then now with the cookies, we have this issue potentially between the client's cookie file and the server's backend database. What if, the entry is inconsistent? then you might have an issue as well. So trade-off in terms of usage, okay, in terms of privacy concern. Trade-off in terms of technical difficulties maintaining the states.
All right, so that was cookie. So it's a little bit like when you were younger, right? Your parents would say, "Hey, if anyone hands you cookies, be careful. Just don't take them." Yeah. So usually, when somebody give you some goodies, be careful. Okay, they might try to lure you into doing something or get stuff. Okay, important or valuable stuff from you. All right, now the final topic today, caches. So these caches, including local cache and web cache, are to improve the performance, particularly the response time. And in some cases, save some network bandwidths sending the web objects. So that's here are the local cache, which is very straightforward and simple.
The next two topics are more about trying to reduce traffic between the server and the client, or trying to reduce the delay downloading a certain object. It's called the caching. So what cache means is to store a temporary copy of certain data. Okay. So conditional get here is like to have a local cache of the web pages that we have downloaded previously. Okay. So the goal is to not send the object again and again and again if the copy we're storing here is already the latest. Okay. Because as a result, we don't need to send the object, and that reduces the delay, and we also reduce the bandwidth requirement. Okay. And so saving the bandwidth is going to be good for everybody. So the way it works is this. Okay. So the first time the client downloads a web page, it's going to keep the copy of the web page on a local cache. So that's somewhere in your local disk. And in the meantime, we record the date, okay, the cache copy is downloaded. And so that when we send a request for the same page again, we carry this special line in the header field, the if modified since, and then the date, okay, of the cached copy, the day we have requested the copy the first time. And then at the receiver side, at the server side, the response will contain the no object if the cached copy is actually the most up-to-date, meaning if the copy at the server has not been changed after the date, then there's really no need to send it again back to the client, okay, because the copy right here is already the latest. So in that case, a special HTTP response message is going to be sent, and the status line is going to read like this. Yeah, 304 not modified. And in the body of the HTTP response message, it's going to be empty. Okay, so no need to send the object. And the way it works is more like this. Let me illustrate. The second time, the client here requesting for the web object sends request message and having this in the header line. If modified since the date the page was downloaded the previous time. And if the server finds that no, it's not yet modified, then send back a short HTTP response carrying the status line. And that's all. No data here. But otherwise, if the object is modified, then we send back a regular HTTP response that says 200 OK in the status line and the web object, the web page again, okay, in the body and the T.
All right, so that was local cache. You save some bandwidth sending the real object repeatedly. Okay, and it might save you a little bit of time there as well. Web cache here is going to help a lot more. So let's hear out how it works first.
Web caches. The purpose is very much like the local caches, but the way it works is somewhat different, but not much different though. Okay. The main difference is this. In local caching, we keep a copy of the object here. Okay. But now we keep a copy of the object here in the web cache, or also known as the proxy server. Web cache or proxy server. Okay. And in conditional get, we still need to send HTTP requests to the original server. It's just that the original server decides whether to send the object with it or not in the response. Okay, sometimes yes, sometimes no. So we save a little bit delay and bandwidth this way. But in web caches, the goal is actually trying to satisfy some client request such that there's no involvement of the original server required. Okay, so some of the clients doesn't need to reach the original server to get the object. And this is done by keeping a copy of the object somewhere in the middle at the proxy server. Okay, so the way it works is this. Users will set the browser such that for all web access, let's go through the web cache. So subsequently, the browsers will send all HTTP requests to the web cache. So send it to the web cache. If the object, the page we're looking for, is already in the cache, proxy server sends the object back. So you see, it works somewhat like a server, but it's not the original server. It's somewhat a delegate of the original server having a copy here. Okay. So object in the cache, cache return objects. Otherwise, the cache here, the web cache here, would request from the server a copy of the object. So this request will be like, the proxy server here behaving like a client of the original server. Web cache there, request object from the original server like a client. Okay. And after the object is downloaded here, the proxy server then sends the object back to the requester. So let me illustrate. If the object is not here, request go to the original server, response comes back, store a copy, and then forward it back to the client. And what's nice about this is, look at this client down below. If the client is requesting the same object, it's a hit here at the cache. Server here sends back the object directly without going through this segment of the internet. So, cache there acts both like a client and a server. As a server, so that it serves the original client, the objects. As a server, because if there's a miss, it will be requesting the original server for a copy of the object. Right? So, some of you might see already, right? A web cache like that is actually preferred by the ISPs, okay, which serves a whole bunch of customers locally. Usually people sitting close to each other tend to prefer fetching or tend to fetch similar content. Okay? So a lot of times ISPs might encourage you to set a web cache on your browser. Now let's go through a few examples to detail why using web caching. Local cache, nice, reduce delay, reduce bandwidth. Through this set of example, let me take you through what is the benefit of doing web caching. In a nutshell, a lot more delay and a lot more bandwidth saving.
All right, so the three scenarios that are coming up, the first two are kind of the two extremes. Okay, let's see the first one.
Good. The example. Setting is this. Servers up here, client down here. So they're part of the institutional network here. And the servers are connected to the public internet. And the internet connects to the institutional network through an access link. Let's assume that the clients here are browsing the web, requesting objects down from the server. The average object size being 100 kilobits, and the average request rate being 15 objects per second. Then multiply the two, you get the average bit rate, coming down this way. Right? And that is 1.5 megabits per second. Now, let's see. Round-trip delay from the institutional router to any of the origin servers and back. That's set up to 2 seconds. And the access links rate 1.54 megabits per second. And the local area network link rate 1 megabits per second. Now with these, we will be able to calculate the local area network's utilization. 1.5 meg divided by 1 gig, that's 0.15%. But here, 1.5 meg divided by 1.54 meg, that's very close to 99%. And that is a problem if you recall. There's this component called queuing delay in the internet novel delay. For transmission over a hop, there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. And the queuing delay is very sensitive to the utilization on the link here. Right. So let me take you here. Queuing delay. Just in case you kind of forget about it. It's very case dependent, and the determining factor is the utilization, which we call back then when we were talking about internet delay, the traffic intensity. So this is amount of input, and this is the output capacity. You see, utilization again. When this is very small, queuing delay also very small. But as it approaches 1, delay becomes large. When it exceeds 1, delay is actually approaching infinity up here. All right. So close to 1, close to 100% delay, just very long. Okay. Let's come back here. Therefore, if we want to calculate the total delay of web request and object download, it will be round-trip delay here, plus round-trip delay here, plus round-trip delay here. 3 components: internet delay, access delay, and LAN delay. Internet delay, we already defined it. Just make it simple. Just say that it's only 2 seconds. But hey, here, fully utilized link with high queuing delay, it's going to be very long. Let's just say that it takes minutes. It could be even higher. And the LAN access delay, now this is very low because utilization is super low. So let's say microseconds, right? So 3 components, which one dominates? Yep, queuing delay on the access link dominates. So bottleneck where? Here, in terms of delay performance. How do we fix this? Let's look at the second scenario. In scenario 2, let's try to address the issue here, because this is the bottleneck link where the delay came from OC. And let's blow it up 100 times. How about that? So using a fatter access link there. The result is that the access link utilization is also reduced 100 times. Less than 1% utilization, you can imagine the queuing delay being very, very short. That brings this component of the delay down to milliseconds. Now, why millisecond? If you recall trace route testings that we did earlier in chapter 1, right? What was that? Quiz 3 or quiz 4, isn't it? Yeah, most of the delay we see between 2 routers are what? Tens milliseconds and maybe 100 milliseconds at most. So if there's not going to be much queuing delay, yeah, the delay is at this scale. So 2 seconds, milliseconds, microseconds, which of these 3 components dominates? Obviously, 2. And from scenario 1, we have minutes of delay, to scenario 2, we effectively bring down the total delay. All right, great. Is there any catch? If you think about it, hey, bringing the access link capacity up 100%, that is actually not cheap. So increasing access link speed, no, not cheap. You need to purchase the new cables, of course, but you might also need to do groundwork. Okay, remove the old cables, install new ones. Just think about the labor cost there. And in addition to that, you might need to upgrade the routers there connecting the high-speed link, just so that you can accommodate potential traffic volume. So, yeah, very costly. Now, in scenario 3, let's see if we could introduce something else instead of blowing up the capacity in the bottleneck link.
All right, so that are the 2 extremes. Third, you will see using a web cache that's gonna give us cheap solution. In the meantime, great delay performance. And this video is gonna run over the end time of the lecture, just about a minute. Okay, so please bear with us.
In scenario 3, instead of blowing up the access link, let's install web cache here. I'm calling it the local web cache because we are very close to the clients. All right. Oh, and yeah, I meant local web cache here. Okay. So that you are not confused with the local cache we've talked about in conditional get, where that cache is actually very, very local on the hard disk of the user. All right. So we are only slightly local here, so to speak. Good. So everything else stay the same. All we did is just install the machine. Now, if I ask you, changing this to 154 megabits per second versus adding a server machine, which one is more expensive? Yeah, you probably guessed, right? Labor costs, routers are expensive, cables sometimes can be expensive depending on the distance between the physical distance between the 2 routers. For your information, this could take millions of new Taiwan dollars. But installing a high-end server machines, it only takes this much new Taiwan dollars. So that's about 2 order of magnitude difference. Yeah. Installing web cache, so much cheaper. Great. Now, let's see if the delay is also going to be better. Or maybe if this is cheaper, then delay is going to be worse. Now, let's try to calculate this. We know the LAN utilization, and so maybe the LAN delay is also about, yeah, microseconds. But access delay, well, we'll have to know the access link utilization in order to estimate the access delay. Therefore, question mark, therefore we couldn't quite yet estimate total delay, right? But then, so this has something to do with the traffic that needs to be brought down this way, right? How many objects will be coming down this way? That seems to be the question. And if you think about it a little bit more, isn't that depend on, for all these web requests we send to the proxy server, how many of them are going to be satisfied locally? Therefore, we could just, transmit the object from the web cache through the LAN to the clients without going all the way up to the servers. So that is this thing called the hit rate. Okay, amount of the proportion of the requests being satisfied locally, that's the hit rate or the success rate. Yeah, let's suppose the hit rate is 0.4. Then we see 40% of the requests will just stay here. Only 60% goes out and back. Great. So we know then the access link here, the utilization is 60% of the access link, 60% of the scenario one. And how much is that? 60% of the traffic, then it's only this much traffic on the 1.45 megabits access link, only 58%. So we cut the utilization from 99% to 58% if we ended up having this hit rate. Now let's calculate the total delay. So 60% of the time it's going to be long delay all the way to the server and back. 40% of the time just on the local LAN. Now, local LAN delay, we've seen earlier, microseconds, but I'm using the milliseconds here just to take into account the traffic here. So if we go out, request object down to the web cache, and then web cache serve the local client, we have one copy down here and another copy down this way. So the LAN here, the traffic potentially could also be higher. So let's use milliseconds just to be safe and take that extra traffic into account. Now, for the 60%, we'll have to go out and back, right? So this is very negligible. This part is what? The key component. This part, 2 seconds, we know for sure. So what's remaining is just the delay here on the access link with 58% utilization. Well, how much delay is this? If there's a lot of queuing delay, we go minutes. If very, very low, only 1%, we go milliseconds. So minutes, milliseconds, well, that's, say tens milliseconds or hundreds milliseconds, right? So I'm trying to be a bit generous here and use 10 milliseconds only. And so total delay here about 2.01. And 60% of that plus 40% of milliseconds. The dominating component is the 2 seconds. So you see here, the overall total delay on average is going to be about 1.2 something seconds. Is this better than scenario 2? It is, right? Scenario 2, you have at least 2 seconds. So what's amazing about web caching is this. The benefit is not just that it's cheaper, but the delay is also lower. And the traffic coming down this way is also lower. Hey, we did not spend any money here, and we also saved some bandwidth here as compared to scenario 1. So there's more traffic can come down this way. Isn't it nice? And that explains why we need web caching, right? It's to reduce the delay. This is also called the response time, okay? That meant the time it takes to issue the request all the way to the server and bringing down the web object. The round-trip delay of the request and response messages. It also reduces traffic, save a lot of bandwidth on the access link, and it's very cheap. Now, an extra benefit we didn't talk about is because we did not assume the uplink bandwidth of the servers being the bottleneck. If the server is poor, meaning having a poor content providers out there, then, let's say that the server here is poor. It cannot afford too high bandwidth uplink. Then reducing the amount of traffic going this way also saves poor content providers some resource, some money. And so web caching there also help the poor content providers to deliver content. All right. And this could be a good thing because most of the NGOs, they might also have information to disseminate, but they couldn't provide good uplink bandwidth. And that actually gives rise also P2P file sharing. The idea of P2P file sharing is also, hey, if I have the copy of the content and another peer grab a copy of it, then this other peer can help serving the other peers. So that peer there is working pretty much like a web cache, isn't it? Like a proxy server. So you could actually think of a P2P network, a network of these proxy servers. Okay. And you saw a bit already. Next slide. Coming next is going to be the second application in chapter 2. And we'll look at how FTP defines its application layer protocol.
All right, so that's all for today. So make sure that you come tomorrow during the break. We'll talk about exam 1, okay, how they're gonna look like and how things are gonna happen, okay, over the 90 minutes of time there. All right. Good. So I see there's a question from Jingwei asking, is the n in the derivation micro or mini? Yeah, it is millisecond. Yeah, so mu there then will be microsecond. Thank you, Kevin. All right, so I guess the content today is straightforward. Okay, so tomorrow we'll talk about email and DNS. These are actually applications that we use every day. Especially in DNS, we'll see really fancy structure, really fancy model in DNS communication. So try to attend tomorrow. And with that said, that's all for this. That's all for today. Okay, bye. Bye, guys.